In this video, you will hear about how to address and analyze contractual requirements, comparing a system and an item approach. Most people we meet in the area of lifecycle management are either working for an organization that's procuring and operating advanced technical systems, or they work for companies that design, build, sell, or maintain the same type of systems. But no one that I've met are doing both. So this means that these people most likely are in business with some kind of counterpart. That in turn means that they probably are dealing with some kind of contract. During this video, you will hear about why it is so important to understand the requirements of such contracts and what they actually mean. To illustrate the topics I wanted to address today, I took a search and rescue helicopter as an example. For this study, I've been looking at a fictitious fleet of 20 flying systems over a period of 10 years. But a real-world system like this can be quite complex. So I simplified things a bit. No, but what I did, and what we often preach, is to select a reasonable set of items to include in the scenario. Because typically, you don't want to bring in structural components or small things like nuts, bolts, or switches, but simply focus on including the stuff that has a failure rate and a frontline replacement task. In this case, it summed up to 120 items over 6 different subsystems like engine, landing gear, flight control system, etc. Now remember, regardless of which side of the playing field you stand in this helicopter program, the provider or the buyer or operator, there will be a contractual requirement that you need to understand and control. A situation that many of you might recognize could look something like this. A contractual requirement saying that we should have at least 90% fill rate. To be able to interpret or analyze how to reach this requirement, we must first understand what it means and how to calculate it. So, to start with, we assume that this requirement goes for each and every individual item, independent of each other. And if we take a look at a definition of the fill rate measure, it would look something like this. The chance of having a spare part available when it is requested. In a world without a time dimension, which is what we often refer to as steady state, the formula would look like this, where X is a random variable for the number of items in resupply. And we can assume that P is a Poisson distribution. These are pretty straightforward calculations, easy to do in any type of spreadsheet. And this is what is typically referred to as the item approach. Using this approach, we can now study the performance of each single type of item separately and measure the fill rate accordingly. To look at the details of this, we can use a graph comparing the fill rate to the number of items that we initially invest in, called stock size. And remember that the target, or the contractual requirement, was at least 90%. And if we don't have any item in stock, the fill rate will obviously be 0. Because if there are no spares in stock, we will never be able to serve any of the demands. If we add one item to the store, what will happen to the fill rate then? Well, it should increase, right? Because we can serve at least some of the demands. And in this case, for this specific item, we see that the fill rate increases to a bit over 40%. But we were looking for 90%, right? So if we add another item on the store, in other words, increasing the stock size to 2, the fill rate goes up to 80%. It's still not enough, so we add a third item, and now the requirement is met. If we take another example, again, we start at 0% fill rate if there are no items in stock. But as we invest in more spares, the fill rate will increase and eventually will reach the requirement of 90%. Now, if we do this for all the 120 items in our helicopter case, we get a distribution of spares looking like this. All dots are above the yellow 90% line. Note, however, that there are no dots on the line for 0 in stock. And that means that we buy at least one of every single item. We can now also look at another graph, which item by item shows that the fill rate for each individual item is above 90%. But what if the contractual requirement actually does not refer to fill rate per individual item, but rather an average value over all items? Then we have something like this, a contractual requirement saying that the minimum average fill rate is 90%. To calculate this, or any type of average, we need to weight the individual values with something. So what would be the most straightforward thing to weight the fill rate with in this case? Well, I hope we can agree that we should use the occurrences of demands per item, and then the formula would look like this. It's still a very simple, or at least straightforward, calculation that can be done in any spreadsheet. So if we look at the spares mix that we just calculated with the item by item approach, what would the average fill rate be according to this formula? And maybe it does not come as a surprise, but in our scenario, the answer will land a bit over 90%, 93% to be exact. And the reason might be obvious, but since each item has a fill rate above 90%, the average value should also be above 90%. Okay, if we are looking at reaching this 90% level as an average over all items, we can reach that in different ways. For example, we could go for 100% fill rate on all items. That would be to overshoot, of course, but we'd still meet the requirement. Or maybe 100% for half of the items and 80% on the rest, and that could still achieve the target. Actually, there are extremely many different ways of doing this. In our scenario, with 120 items on the helicopter, and let's say that we have two options on the number of spares for each type of item, we'll get 2 to the power of 120 alternative, which means 1.3 with 36 zeros. Well, now we are out of my comfort zone when it comes to using spreadsheets. So we have to be smart here. And a good idea could be to use an analytical software. As a coincidence, I happen to be acquainted with such a software. But more about that later. Being smart is anyway always a challenge. So how do we do to select one of all those alternatives? Well, obviously we need some more criteria because many of the alternatives will give us the same total value. I think most of you can agree that such a criteria should have something to do with money. So let's bring in cost as a decision parameter. If we can select the mix of spare parts in a way that minimizes the total cost of buying and owning these spares while still reaching the targets of the contract, everyone would probably be quite happy. Now we have a different way of looking at things, and this is often referred to as the system approach. With this approach, we prioritize between different individual items, while also minimizing the total cost. This means that we will put a higher risk on some of the items, but from a system perspective, it can be worth some savings on these items because they are not requested as often. On the other hand, items that are requested more often will also contribute more to the average fill rate. Therefore, we should invest more in spares for such items because it's going to be worth it from the system perspective. To summarize, we want to maximize the fill rate while minimizing the cost. And if we go back and look at the stock assortment that we calculated to reach the first requirement with a minimum fill rate per item, it looked like this. And if we compare that to an optimized spares solution according to the system approach, we can see that we get a totally different spares mix. And what we see now is that some of the items goes below the yellow 90% line. You can even see that a bunch of them ends up at the bottom of the graph with 0% fill rate. That's because we choose not to put any of these in the store. Probably because the demand is very low and we are willing to take a higher risk for those items. But there are also some items that we select to buy more of. Again, because they have a higher impact on the average value for the entire system. Comparing items individually between the two approaches, since we'll show it even clearer. For example, for this item, we go for a lower stock size with the system approach, which also results in a fill rate below 90%. For another item, we calculate a higher stock size with the system approach, therefore getting a higher fill rate. And for a third example, maybe we don't buy any spares at all, so the fill rate goes to the bottom for this item when using the system approach. And as I said before, it's obvious that we also need to include cost as a variable when evaluating our contracts. There are potentially many different costs associated with spare parts. You don't only have to buy them, you probably have to store them, transport them every now and maybe even maintain them. And all such things cost money. If we look at the spares assortment from the item approach and we calculate the associated cost for that, and then put it in a cost effectiveness graph, we'd get this. As you recall, we got an average fill rate around 93% in that case. The corresponding cost for this spares solution would land just above 65 million if we look at the entire life cycle for the helicopters in our scenario. Now, the big question is, and this is where it gets really exciting if you ask me, if we look at the results from the system approach, what would the achievements look like then? Well, to start with, let's focus on the same level of overall performance as we got from the item approach, meaning that we stay around 93% fill rate. Now, and keep in mind what I said about having to be smart. Looking at the spares assortment that we produced with the system approach, can that solution achieve the level of fill rate in a cheaper way? Yes, it can. In our helicopter example, we can actually decrease the cost for spares from 65 down to 37 million. That's like 40% saving. Now, what if we could use the same spendings needed to reach the requirements for the item approach, the 65 million, but applying the optimization from the system approach instead? Well, it turns out doing that, we can make a significant improvement in terms of average fill rate. For the same cost, we can actually go from an average of 93% to almost 99%. That means another 6 percentage points. And do you know what? I'm going to confess something here. Well, comparing item and system approach like this, well, it wasn't my idea from the beginning. No, people have actually been doing this for quite a long time. For example, a former colleague from Systicon, Mr. Ole Våk, wrote a true masterpiece on logistics engineering many years ago, and one of the studies in there showed how going from an item to a system approach on average could save 20 to 30% on spares cost. And it's not only him. Another example is the more famous Mr. Sherbrooke, who also concluded savings of the same order of magnitude going from an item to a system approach. Now, am I being an idealist? Yeah, maybe. Well, I mean, of course, in real world, there will always be exceptions and extraordinary events. But remember, here I'm talking about long-term strategic analytical decision support. But that doesn't mean that this isn't interesting. Quite the opposite, actually. With sensitivity analysis, what if and worst case scenario testing, we are able to get a pretty good picture of the robustness of the solutions produced by the analytics. And I've met many people who says things like, but I know for a fact that we need at least one of this item in store. And I go, sure, no problem, let's add that as a restriction. And then someone else come and say, hey, but this specific group of item is really critical as compared to those others over here which aren't. And I go again, sure, no problem, let's set individual requirements for those specific items to make sure they are prioritized. But remember, every time you put in a constraint like this, you will also constrain the cost-effective optimization. So, anyway, better to plan than to wait and see. Fill rate, which I've talked about so far, tells us how often requests for spare parts can be satisfied. And that's great. From a warehouse perspective, right? Because it measures the performance of the store, but it doesn't say anything about how many of the previous requests that has been served. This in turn means that we have no idea if there are any requests in the queue, and if so, how many. In other words, the only thing the fill rate answers is, do we have a spare part or not? But why is this a problem? Well, quite often it's the actual operations of the system that is important. So things like how many helicopters are actually ready for takeoff. And if we are interested in measuring something that's closer to the operations of the systems, and not just measuring the performance of the warehouses, we need another KPI. So let's introduce what's referred to as system availability. And availability is defined as the fraction of our fleet of systems that, on average, is ready for operation. Looking at an operational effectiveness KPI like availability, our contractual requirement could look something like this. We need an average of at least 16 out of 20 helicopters ready for operations. In other words, having an availability of 80% or more. Again, we keep the system approach because that seemed like a good idea, right? But now we go for maximizing the availability and minimizing the cost. To compare different solutions, we once again turn to a cost effectiveness type of illustration, and this time comparing system availability with associated costs. The blue dot here represents a spares suggestion produced with our previous method, where we were maximizing the fill rate. Given that method, the dot shows the cheapest way of achieving the requirement of 80% availability, meaning an average of 16 available helicopters. Now, if we instead shift the focus of the optimization from fill rate to availability, we may actually achieve our target for a substantially lower cost. So how is that possible? Well, since an availability requirement is calculated in a different way compared to fill rate, we should also probably select our mix of spare parts in a different way. And again, with that kind of clever software I was talking about before, this kind of switch is just a single click away. And one last comparison. If we have funds allocated for spares according to the first estimate here, that's around 26 million, it's actually possible to increase availability considerably. Going from 80 to 87% actually means that we, on average, can expect one more helicopter being ready for operations. I'm not saying that it's always better to optimize for availability. It could very well be the other way around, but it's important to have a clear vision on what the requirements are in order to know what you are steering your analysis and optimizations against. If you don't have the right target from the beginning, the results simply won't be the best. Let's wrap this up with 3 conclusions. 1. It's important to understand the KPIs of your contracts. 2. Through different type of estimations and analysis, it is possible to control and follow your KPIs. And 3. It's really important to go for KPIs that reflects the value creation in your organization. If you want to know more about Opus Suite, then visit our website or contact your nearest Systicon branch or Opus Suite representative. We'd be happy to give a live demo or any further information. Thanks for watching.